Most drone designers choose propellers based on thrust or efficiency data alone. Aerospace engineers, however, take a different approach. I will show you which metrics they actually use and run tests to prove why thrust and efficiency alone aren't enough for your drone design. This is the same kind of testing engineers at institutions like NASA and MIT use to predict real flight performance. You can use the same easy steps to get metrics that will allow you to go above and beyond when you're comparing different drone components. All you need is a flight stand, a wind tunnel, and the flight stand software. We'll go through the input transformation tab of the flight stand software and input these formulas: thrust coefficient, torque coefficient, power coefficient, Reynolds number, and the advance ratio. If you don't have a flight stand or wind shaper, that's okay. You can still follow along with the guide using the simulated board in the software.
Now let's go pick our components. There are a lot of different propellers to choose from, and when you go to Google, you'll find a lot of content on smaller propellers for hobbyist drones, and not much content on larger propellers, which is what we're going to be tackling in this video. Why? Because there's a lot of differences in terms of characteristics for larger propellers and smaller propellers. So in this case, I'll be running my test using this 28-inch Majlik propeller, but we're not just stopping at one. I'm also going to be running the test on this 26-inch Majlik propeller to show how changes in the diameter can affect the performance characteristics. We're using the Flightstand 50 Pro, which can measure up to 50 kgf of thrust. It's perfect for this setup. Once you have the motor and propeller attached, in this case we're using a 105 kV motor from Zor, then use an appropriate ESC to control the motor, and of course the AC/DC power supply. Now let's talk about the wind tunnel in the room. So this is the 6x6 wind shaper. The reason why it's called the 6x6 is because there are 6 fan modules in the vertical axis and 6 fan modules in the horizontal axis. That's 324 fans in total. This thing is massive. And each fan module is able to generate up to 16 meters per second of wind speed. Now for a little background. We read through dozens of research papers about propellers and drones from researchers that use our equipment, and we kept on seeing propeller coefficients and advance ratio to characterize and compare propeller behavior. And we asked ourselves, what does plotting against advance ratio actually tell you that a simple thrust versus rotation speed graph can't? So we wanted to run our own experiments to find out. First off, in the drone world, efficiency is often expressed as grams force of thrust per watt. This is a useful and practical comparison, but it isn't the aerodynamic propeller efficiency engineers normally refer to. What we want is unitless normalized value to compare propellers. First, there's the Reynolds number. Without going into much detail, the Reynolds number shows us which regime of air the propeller is operating in. It's the ratio between initial forces and viscous forces in the airflow around the propeller. This will come in handy later on. Then there's thrust, torque, and power coefficients, which all tell the same story from different perspectives. The thrust coefficient is a dimensionless way of expressing thrust that accounts for air density, propeller diameter, and rotation speed. Now apply the same concept to the torque coefficient, and you get the torque requirement normalized in the same way. Finally, the power coefficient does the same for mechanical power delivered to the propeller. To make sense of all of these, we need another variable to compare all of these values. Engineers typically use advance ratio. This is also a unitless value that tells us how fast the aircraft is moving forward relative to how fast the propellers are spinning. More specifically, advance ratio evaluates forward flight speed in proportion to the propeller's rotational tip speed. If you want a deeper dive into the math and application of these values, we actually wrote an in-depth article on this, which you can check it out in the link in the description. Now that we have the theory out of the way, let's get this propeller spinning and see what the data actually tells us. Before we begin the test, by default the Flightstand software does not output these values. But what you can do is use the input transformation tab to generate these values on the fly. This will take those raw signals and turn them into performance metrics automatically. Simply go into the input transformation tab and let us first define some constants that we will be using throughout the setup. I'm going to input the air density. In this case, we're using standard air density at sea level and the propeller diameter. I've also added the viscosity of air, which will be used in the Reynolds number calculations. Next, I'll start building my formulas. Let's start with the Reynolds number. We'll click Add New Transformation, name our transformation, input the formula, and select our previously defined constants. Hit save, and there we go. Alright, now that I have the data, let's see what's happening.
We performed a step test at constant wind speed with the flight stand, and each data point represents a recording from a different throttle point.
As expected, the 28-inch prop is generating more thrust at all the throttle points, even with the wind blowing. Let's skip ahead to the results at maximum wind speed, 17 meters per second. This is where we start to see negative thrust due to the high wind speed and the windmilling regime observed at these lower RPMs. Moving up the rotation speed, again, the 28-inch prop is producing more thrust. However, as mentioned, the gap between the thrust is now lower because of the wind. The reason for this comes down to something called the advance ratio. What's happening here is that at high wind speeds, the advance ratio increases, pushing both propellers closer to their zero thrust operating point. Let's quickly take a look at the efficiencies of these propellers. In the middle of the graph, we see that both propellers have roughly the same peak efficiency. This makes sense, as the props are already pretty close in size and are made by the same manufacturer. However, if we look at the end of the graph, we can see that the larger propeller is more efficient at lower RPM. But efficiency starts to drop off as RPM increases. And based on what we already see here, I bet that if we continue testing at higher RPM, the 28-inch curve would continue to drop off faster than the 26-inch curve. This makes sense, as larger propellers typically reach peak efficiency at lower rotational speeds than smaller propellers. But these graphs still aren't giving us the full picture. So let's move on to something that will give us a deeper understanding of these performance differences, the propeller performance coefficients. Now let's look at the thrust coefficient plotted against the advance ratio. Here we have a 1700 microsecond throttle input. What we see is that as the advance ratio increases, meaning the incoming airspeed becomes larger relative to the propeller's rotational speed, the thrust coefficient decreases for both propellers. But notice something interesting. The 26-inch propeller reaches a thrust coefficient of 0 at around advance ratio of 0.23. At that operating point, the propeller is no longer producing net thrust. It's essentially just being driven by the airflow. The 28-inch propeller, however, still maintains a positive thrust coefficient at that same advance ratio. In other words, it can continue producing thrust under high forward velocity conditions before reaching the windmilling regime. And that difference can matter in real aircrafts. It means the larger propeller maintains useful thrust at higher airspeeds or stronger headwinds where the smaller propeller is already approaching its zero thrust conditions. As a drone operator, you can use these graphs to determine which prop is better for you depending on the flight conditions. If you look at the torque and power coefficient curves, we see that the 28-inch propeller also operates at higher torque and power coefficients across much of the range. This means that at the same operating conditions, it requires more torque and mechanical power from the motor. That's expected for a larger propeller disc interacting with more air. In practice, this highlights an important trade-off. Larger propellers can maintain thrust at higher advance ratios, but they also demand more torque and power from the propulsion system. So why do we see this difference between the two propellers? One factor is the Reynolds number. If we plot the Reynolds number at 1700 throttle input, we see that the 28-inch propeller operates at consistently higher Reynolds number across all wind speeds and advance ratios. Reynolds number represents the ratio of inertial forces to viscous forces in the airflow over the blade. Higher Reynolds number generally means that the blade airfoil section operates in a more favorable aerodynamic regime. In practical terms, this typically allows the blade section to generate lift more efficiently and with lower relative viscous losses. So let's summarize our findings. At first glance, we saw that the 28-inch prop is producing more thrust at varying rotation speed and wind speed. Then the efficiency graph showed us that they were surprisingly similar to each other. But when we dug deeper with the propeller coefficient numbers, we saw that the 28-inch endured for far longer than the 26-inch in strong wind conditions. But this experiment wasn't perfect. So let's talk about some of the limitations and what we could do differently in the future. So first things first, as I mentioned earlier, we didn't capture the behavior of the propellers across a large range of advance ratio. We tested our propellers at 5 different wind speeds with fairly large speed steps. Because of this, we weren't able to capture the full shape of the thrust coefficient versus advance ratio curve. Our test started at relatively high wind speeds, so we were already operating at high advance ratios, where the thrust coefficient begins to decrease. If we instead looked at the zero wind case and plot thrust coefficient against RPM, we see a slight increase in the thrust coefficient with rotational speed. This is likely due to the Reynolds number's effects. As RPM increases, the local blade Reynolds number increases as well, which can slightly improve the aerodynamic performance of the blade sections. In other words, the apparent increase in thrust coefficient isn't because RPM alone improves performance. It's because aerodynamic conditions around the blade are changing as Reynolds number increases. In a follow-up experiment, we could select a narrower range of wind speeds to target more specific operating regime. And our equipment permits this. The windshaper gives you incredible granular control for the wind speed. Another limitation was actually our maximum wind speed. Advanced ratio depends on relationships between airspeed, rotational speed, and propeller diameter. To reach very high advanced ratios with large propellers spinning at thousands of RPM, the incoming wind speed must be extremely high. For example, to reach an advanced ratio of 1 on our 28-inch propeller at 3600 RPM, we actually need a wind speed of 42.6 meters per second. That's over 150 kilometers per hour. The windshaper can achieve these speeds as long as you have a convergent with your setup. We were also limited by our power supply we had available. The day before our experiment, bam! The power supply crashed out, so we had to go with a smaller one, which was limited to 45 volts. We achieved the maximum rotation speed of around 3,900 RPM, though our propellers are rated for up to around 6,000 RPM. Our motors can normally handle up to 66 volts, so the test was voltage limited. Those are some of the more obvious limitations of the setup, but let us know in the comments if we missed anything else. To wrap things up, this experiment was a lot of fun for us, and hopefully for you as well. We hope that we've demonstrated the value of these 5 propeller performance metrics, which allows us to compare propellers across different sizes, rotational speeds, and operating conditions using the same dimensionless framework. We're excited to put our windshaper to work with even more experiments, so let us know what type of drone or propeller test you'd like to see. And with that being said, thanks a lot for watching, and we'll see you in the next video.